Hello class, this is Mrs. Clark. This video is just meant to give you an introduction to some things we were not able to get to in class on the first day of absolute value functions. So today we're going to talk about transformations of absolute value functions. So today we did learn how to graph an absolute value function and how to analyze key attributes based on the structure of the function. Now, we did whiteboard practice and you all showed me how that you can find the vertex, the axis of symmetry, and the domain and range. So good for you. Those are going to be very valuable lessons now and all year in Algebra 2. But what we didn't get to was transformations. Now, what are transformations? Well, we talked about the parent function in today's class, but what happens when we change certain parameters on the parent function? What happens if we do not have the most basic form of the function? Well, transformations are what's happened. When we apply transformations, two things occur. The graph can change. The location of the graph, it could shift up, down, left, or right. The graph might be reflected and open downwards. The graph might get wider or more narrow. All kinds of things can happen to the graph as a result of transformations. And when the graph changes, some of the attributes change too. It's very possible that your vertex will change and your axis of symmetry will change, and maybe even your range will change based on what transformations have been applied. So, okay, let's look at the specific parameters that make up all the transformations for any function you will ever study. So we're going to start with the absolute value parent function, and we're going to name that function f of x. Then we're going to go to the general form of the function, and we're going to use function notation. Now, what this means is that if the function f is the absolute value of x, then we can change the parameter a, b, c, or d. Now, we're going to look at each of these parameters one at a time. But before I go there, let me make sure you have a basic understanding of how to use and read function notation. Okay, so we started function notation by naming a function f, and we have f of x is equal to the absolute value of x. And if that is true, then a times f of x is equal to a times the absolute value of x. So I can make a any number, 0.5, 1/2, 3, 14, -1, but it is the parameter a that I'm talking about. If f of x is the absolute value of x, and I go with f of x minus c, that means I'm taking the input of my function f, and I'm subtracting some number c to it, from it. And the last example, and these are just examples, if I have my function f, which is the absolute value of x, and I add some number d to it, then I'm actually adding d to the absolute value of x. Now, hopefully that will clear it up for you just a little. If not, we will look at this again in class. Meanwhile, let's look at what changes to the parameters a, b, c, and d actually do to the parent function. Okay, now remember, f of x was the absolute value of x. What happens if I subtract some value from x, the input x, inside the absolute value bars? So I'm going to show you this graphically because it makes a lot more sense when you can see what is going on. Now, what happens is a horizontal translation of the graph, right or left, c units. So if I have x minus 2, it's going to move to the right 2. If I have x plus 2, it's going to move to the left 2. Now let's take a look at this. In this graph, you'll see the function notation over here on the left-hand side. I use Desmos to do this. The red graph is the parent function, so you can compare what has happened to the parent function when I change the parameter c. In the blue graph, I changed the parameter c to 4. So I just put a 4 in place of the c, and I have x minus 4. That means c, the value of c is a positive 4. This will horizontally translate the parent function 4 units to the right. Meanwhile, if c is negative 3, let's say c is negative 3, then I have x minus negative 3. That's going to resolve to x plus 3. That's what I have here. So this is really x minus negative 3, which you all know will resolve to be x plus 3. But because the value of c was negative 3, it shifted my parent function 3 units to the left. All right, let's go on. What happens if I just add a number to my absolute value function on the outside of the absolute value? Well, that parameter is d. And here's what d does. It shifts the graph up or down d units. If I have plus 7, it's going to go up 7 units. If I have minus 3, f of x minus 3, it's going to go down 3 units. Now let's look at this in a graph. Again, the parent function is the red function. Now, if I add 2 to my parent function, I'm going to shift the whole function up 2. That's the green one. If I subtract 3 from the parent function, I'm going to shift this whole thing down 3. Now you notice it didn't shift left or right. It didn't change its width or anything like that. It's just shifting up or down, which of course will change the vertex. You know, the previous change that we looked at, shifting it left or right, will also change the vertex. But this change here, d, up or down, will also change the y value of the vertex and the range. Now we'll go into that in depth in the class. The next parameter we want to look at is the parameter a. In this case, we just take some number and we multiply our whole function times that number. So this would be the same as, let's say, y is equal to 3 times the absolute value of x. So let's take a look and see what happens. That will result in a vertical stretch or a vertical compression. Now, one way to look at this, but it's not academic language, but if I were just going to put this in plain English, I would say that the graph is going to get more narrow. That would be a stretch, like you're stretching a rubber band up. Or it's going to get wider. That would be the compression, like you're sitting on a water balloon and pressing it down. So let's take a look at the graph and see what happens. Okay, so again, the red graph is my parent function. I'm going to take that whole thing and multiply it by 4, and that's the green graph. And you can see it's increasing. The slope is bigger, and it's increasing at a higher rate. As a matter of fact, it's increasing by a rate times 4, by 4 times more than the parent function. If, on the other hand, I'm looking at a fraction here between 0 and 1, that is a vertical compression, and it will change my slope of my parent function from 1, up 1 over 1, up 1 over 1, to 1/3. Up 1, 1, 2, 3. Up 1, 1, 2, 3. So instead of increasing at a rate of 1, it's increasing at a rate of 1/3. Again, don't worry too much about a total understanding of this. We will go through this in gory detail in class. All right, now what happens if A is negative? A could be 1, by the way. If there's nothing in front of f of x, then it is 1. But what happens if you have a negative 1 times f of x or negative 3 times f of x? What happens? Well, what happens is a vertical reflection. We talked about this a little bit in class. So if red is my parent function here, the orange is just a straight reflection of the parent function. All I did was put a negative sign in front of the function. So in this case, A would have its default value of 1. But if I combine that with a value such as 1/5, then I get the vertical compression, which makes it wider, in addition to the vertical reflection. That would be the black graph right here. Right here. All right, last, we're going to take a look at the parameter b. Now, b operates on the input x. It's a multiplier on whatever your input is inside the absolute value function. Now, it is a horizontal stretch or compression, and it too makes the graph either more narrow or wider. Now, let's take a look. B operates a little bit differently than A. First of all, this 8x would be inside the absolute value bars if I was using that function here. And you can see that it makes the graph more narrow, as opposed to 1/2 x, the multiplier 1/2, which makes the parent function wider. Now, we will develop a complete set of notes so that you understand exactly how this works in class, so don't worry too much about it at all. I just want you to have an idea and have heard these terms before. Now, we can also have a reflection, a horizontal reflection. So if B is negative, that's what we have, a horizontal reflection. But because the absolute value function is symmetrical, you don't see any visible change unless there's also a B value, like in our case, 2, a negative 2, which gives us a horizontal reflection, but it doesn't change the graph at all, other than to make it more narrow, or 1/4, which makes the graph wider. But we don't see the reflection because it's symmetrical, so it's just kind of reflecting on itself. Now that's all. I hope that you got a little bit out of this video, and we can start talking about transformations right away, and I can clear up any confusion you have, which I'm sure after this not so great video, you have some confusion. But believe me, this will give us a head start on clearing up things for you. So thank you for watching the video. Make sure you mark this Google assignment turned in when you're done, and I will see you in class on Wednesday. Peace out.